Okay, so now keeping in mind the two things that we have learned, what was the first thing? The first thing we learned was how is a magnetic field, or what are the pattern of magnetic field lines around a straight current carrying wire. This you remember, in the form of concentric circles. What does that mean? Circles with one single center, and in the center is that wire. If I have to remind you about it, it was like this. If this is our wire, and you remember we kept this piece of paper and we made a hole in it. Actually, we made this hole, we kept this piece of paper, and this wire was actually connected to a circuit, a battery, and everything, all of that. And then we had just spread around iron filings randomly like this. Then we completed the circuit and we gently tapped the iron filings, and we saw the iron filings, they arranged themselves in the form of concentric circles with increasing distance between them as you go far from the wire. So we learned that in case of a current carrying wire, how is the magnetic field lines? They are like this, right? The magnetic field lines are formed like this. What are these lines? These are the same lines that we had made in case of a bar magnet, like this. You remember? Like this. They and exit from the north, enter from the south, straight line. You remember, right? So it is the same lines that we are drawing, magnetic field lines. That was in case of a bar magnet. This is in case of a straight current carrying wire or conductor. Then the second thing we learned was about the right hand thumb rule, which means if the current is going in this direction, if I show you that in this wire I direction is this, then we see that the direction of magnetic field lines is given like this, from right to left or anti-clockwise. So I make the lines like this it goes. So it is complete circle. So like this is it is going in the form of circles, right? Now, keeping these two things in mind, we are going to study the topic that we are going to do now is magnetic field lines by a current carrying circular loop. Okay, those two things are the only things that are going to be used here also. Let's see. So let's read in your PPT and then I will explain it to you. So it says here, at every point of a current carrying circular loop, the concentric circles representing the magnetic field around it would become larger as we move away from the wire. This I have already told you. Why? Because we have seen that in every case, as we move farther and farther away from whatever is generating the magnetic field. In case of a bar magnet, what is generating the magnetic field? The magnet. In case of a wire which carries current, what is generating the magnetic field? The current carrying wire, the current in the wire. So as the distance from that thing increases, the strength of magnetic field decreases. And how did we know that? Because the distance between the magnetic field lines increases, and we had learned in the properties of magnetic field lines that when the field lines are closer together, magnetic field is stronger. When they are farther from each other, the magnetic field is weaker, right? So here it says, at every point of a current carrying circular loop, the concentric circles representing the magnetic field would become larger and larger as we move away from the wire. Okay, we know about this now. But how do we calculate the magnetic field of the whole loop? So if you just want to not look at the figure right now, I will explain it to you first and then it would make complete sense to you. Okay, so just imagine that there is one straight wire. This was the straight wire that we had been studying for so long. Current was going through the wire. Now what I have done is I have taken this same wire and just bent it in the form of a loop. Okay, so that is not going to change how the way current flows through it and what we had studied about the right hand thumb rule and the magnetic field lines due to a straight wire. How? Look. So if I draw this a little bigger, if this is my loop, okay, this is my loop, okay, I have connected this loop to the battery so that there is current through it. I have connected it through a key. I have kept the key open right now. So right now there is no current in the wire, thus there is no magnetic field generated. So, okay, this is the imaginary plane that on which I am going to show you the magnetic field lines. Okay, great. So think about, if we close this circuit, which direction does current flow from? It flows from the positive terminal of the battery to the negative terminal, right? So current flows from here here, from here it goes, and it is flowing in the loop like this, right? All the way from here, here, through the circuit, and it comes back to the negative terminal. Great. This much we know. Now, what we have to do is, we don't have to calculate the magnetic field lines at each and every point. Let us take these 2 points, okay? This point A and this point B. Okay. Now, if you see at this small point, you remember in case of mirrors when we were doing, when we had to draw the normal at one point at the mirror, we took this small piece of the mirror and we drew it at that point, right? So I am taking these two small pieces of this circular loop. This whole circular loop, I am just taking two pieces where this A and B are, okay? Consider them points or small pieces of the wire. So if we are considering them as points here and here. So what we do now is we apply the right hand thumb rule as we know. Okay, so come to point A. At point A, which direction is the current flowing in? In upward direction. So tell me, how are we going to hold our hand for the right hand thumb rule? Right hand, thumb in the direction of current, right? So thumb like this and we hold the wire like this. So which direction are my fingers curling in? They are going towards. Now look at which direction the tips of my fingers are pointing in. They are pointing towards left, right? That means from right towards left, right? These tips of my fingers are pointing towards left. So the magnetic field lines would be from right to left or anti-clockwise. So first, let me draw the shape of the magnetic field lines around the wire. How is it? In the form of concentric circles. So by now, all these things should be at the tip of your fingers, okay? So we draw it like this with increasing distance. Let me just draw 3 right now, okay? Now I draw the direction in which the magnetic field lines are. Again, the current like this, from right to left, my field lines are going. So I draw the arrows, okay, like this. So now it shouldn't be confusing to you that in this direction, here in this part, it looks like it's going from left to right, because I've already shown you how it would look like if it was going from left to right, okay? So if you have a doubt about that, go back to that slide and watch that again, okay? I had drawn a third magnetic field line here. So this is the direction of my magnetic field and magnetic field lines. Great. Now I come to point B. Now think, in this part, where is my current flowing? The current is flowing in a downward direction. Okay, I point my thumb down. Then, which direction are my fingers curling in? Look at the tips of my fingers. You have to do this yourself also, students, or else you'll get confused. Okay, don't just look at me. Do it yourself also. So, which direction are your fingers pointing in? The tips of your fingers, where are they pointing? They're pointing towards the right side, right? That means the magnetic field lines are going from left to right. Okay, keep that in mind. So again, I draw just the concentric circles. I just draw 3, okay? Okay, now they are going from left to right. That means like this. Wait. So what does from left to right mean? This is my left. For this part, this is my left, right? And this is my right. So the arrows are going from left to right, like this. Here we have to look at, right? So if this is going from left to right in this direction, obviously the arrow would be down here, right? It is going in one same direction only. So we don't have to get confused by from the other side. If your fingers are pointing towards right, you would draw it from left to right like this. You would go to the left and you would draw the arrow going towards the right. If you see it is from right to left, look at in this case, in the case where we drew it for point A, this is the left, this is the right. And we saw that our fingers are curling from right to left. So I go to the right hand side, I draw the arrow such that the field lines are going from right to left. Then I don't get confused because here it seems like it's coming from left to right. No, don't think about that. So in this case, my fingers are pointing from left to right. So I go to the left side, I draw the arrow going towards right, so it would obviously go in this direction because it has to keep going like in a continuous circle. Okay, then here also the magnetic field lines are in the same direction like this, and this is how it is. Now think about this. If I keep going, if I keep making another, I make one more circle here, then I make one more circle here, and I keep going like this. So if these circles keep getting bigger and bigger, here I've taken this L. If I have to tell you this piece of paper, if I take this, if I take this as L, M, N and O. So here I have restricted myself to this small piece of paper, right? But the magnetic field keeps going till infinity. Yes, the field lines keep getting very far from each other. So the effect of the magnet is less, but they are not restricted to this paper. It can go, it is going like this also, outside the paper also, right? Whole throughout the screen it can go, right? So just think about this. If these keep getting bigger and bigger, these magnetic field lines keep getting bigger and bigger, at one point it would look like a straight line. What am I relating this to? You remember here in case of a bar magnet, we had said that when this loop becomes very big, it appears like a straight line at this part, right? So what I'm trying to do here is relate this to something that you already know and something that you've already learned, right? So if keeping this concept in mind, like a bar magnet in which this, when the curve is very big, it looks like a straight line. So here also in the middle, when these circles become very, very big, say like this, right? So it almost looks like a straight line at the middle point of these two points A and B. So that is how we represent this. In the middle, we show the magnetic field line like this, one straight line. Now, can you tell me which direction the magnetic field line is going to be here? You can see to the left of this, the magnetic field is like this. To the right of this line, it is like this only. So obviously it is going to be in this direction only. So it is clear to you now that in the middle, actually, even though it looks like at point A and point B, the magnetic field lines are in opposite directions, at the middle point, they actually merge to go in the same direction only. Okay, so take your time, draw the field lines by yourself using your hands and using right hand thumb rule, and make these loops very big so it would look like a straight line in the middle. Then see that they're actually pointing in the same direction, the magnetic field line from A and the magnetic field line from B. Okay, so don't get confused at any point, go step by step and it will all make sense to you. Great, moving on. So Maxwell's corkscrew rule, this is just another type of rule that you can use to determine the direction of the magnetic field. It is preferred, and I would say that you use the right hand thumb rule. That is the more accepted rule, and even in answers, if you have to write the direction of magnetic field line was determined using the right hand thumb rule. So this is just an additional rule. So here it says that if we consider ourselves driving a corkscrew in the direction of the current, then the direction of rotation of corkscrew is the direction of the magnetic field. That means if this is the current, again you use your right hand only, and you are rotating the corkscrew. How do you rotate the corkscrew? You always go towards the right, right? So if this is the current and you rotate it like this, then the magnetic field is in this direction, clockwise, right? So this is just an extension, you can say, of the right hand thumb rule. You can or cannot use it if you want, but I would say that you use the right hand thumb rule preferably. Okay, great. Now, magnetic field produced by a circular coil. This is just what we did right now. So here, as I said in that derivation or in that slide, we just calculated it at 2 points A and B. So in this figure, it is showing it to you at every single point. Okay. So this is just something that you need to know. So let's read here. So don't get confused by these many white lines, right? So you remember this loop that I had made, this loop that I had just made, I had said that I am calculating it at point A and point B, not at every single point on this loop. It cannot be calculated if there is a point C here. Then if the current, if I remember correctly, it was flowing like this. So at point C, which direction is our current flowing in? Like this. So the magnetic field lines would be like this, right? So at every single point you can calculate it, but Just for understanding it and just for simplicity, we calculated it at points A and B. Now let's read what your PPT says, keeping all that in mind. So it says that if a circular coil having n turns has n turns, what does that mean? I took one wire, right, and I just bent it into one loop. But if I take a wire and I bend it many times and form it into a spring, then it is a circular coil having n turns. Okay, so it says if a circular coil has n turns, the field produced is n times as large as the field produced by. So I had bent it into one turn. So if we bend it into n turns, what would happen? The magnetic field would just be multiplied, right? If we, right, because of one turn, the magnetic field that is produced, the magnetic field due to n turns would be into n times the magnetic field due to one turn. That is pretty logical, right? So that is what it's saying, that the field produced is n times as large as the field produced by a single turn or one turn. Okay. Then it says that this is because the current in each circular coil, so it says this is because the current in each circular turn has the same direction and the field due to it just gets added up. What does that mean? Look, if we have two wires here, if we have two wires, current carrying wires like this, okay, this is I1, this is one wire, and this is I2, this is another wire. So what happens in this case is, if this is our direction of magnetic field due to I1, no, let's take the direction of I2 as downwards, okay. Why I'm taking this, it would make a little more sense to you in a bit. So if this is I2, first if I look at I1, I drew the concentric circles. What would be the direction of magnetic field lines? From right to left. Okay, so I go towards the right, I make the arrows going towards the left. Okay, so obviously there is a continuous circle, so it goes like this. I'm just removing this I1, it's making it very messy. Okay, I'm writing I1 here. Okay, so it goes in this direction and then like this. Great. Now I2. Again, I'm removing I2 from here. I'm just writing I2 again. So these are the lines. I2 is in the downward direction. Now, downward direction from left to right. Okay, so I go towards the left. I draw my arrow and it is a continuous circle. So it goes like this. Now, students, look at this area. In this small area, both the magnetic field lines you can see point towards the upward direction. So what does that mean? That means that the magnetic field due to I1 and the magnetic field due to I2 get added up, right? When two things are going in the same direction, if I am walking towards one direction and someone pushes me in the same direction, so I would keep walking even faster, right? So that is the same logic that we are using here. Because they are in the same direction, the magnetic fields due to I1 and I2 are in the same direction, they get added up, right? But in case of a circular coil, there are not I1 and I2. There is the same current flowing throughout the circular loop, right? Because it is one loop connected to one battery. So this is actually like this. If I look at it now, if I explain it to you from here, if you remember, this was the current in the loop. Now if you look at point A and B again, can you see that the direction of current flowing in A and B is actually opposite, right? And then we also saw that in the middle there is one common line that we can draw. What does that mean? That means that the magnetic field because of point A and the magnetic field because of point B actually added up to form one magnetic field going in the same direction. Okay, that is what it says, that the current in each circular coil has the same direction and the field due to each turn just gets added up. The field is in the same direction finally also. Okay, great. Let's move on.